Good luck, everyone. Pulse propagation. How does that look? Numbers, pulses, configuration, broadcaster. Okay. Is it not doing it? Okay. Oh, this is yesterday's data. Okay. Not sure what's going on here, but that looks like yesterday's data. Okay. Okay. Day 20. Several types of module. Flip-flops are either on or off. If I see high pulse, okay, ignores it. Low pulse, okay, yeah, flip-flop. Between on and off. Off, it turns on. Okay, conjunction modules. Remember the type of impulse received from each of their input modules. Default to remembering a low pulse impulse for each input. Impulses receive the conjunction will first update memory, then for that input, then if it receives a high pulse and the low pulse, otherwise, yeah, so that's an AND, but okay, but with memory. There's a single broadcast module, broadcaster, when it receives a pulse, it sends it to the same pulse to all of destination modules, a single button called button module. When you push the button, a single low pulse is sent directly. Single low pulse sent directly to the broadcaster module. Okay, so broadcaster is where it starts. After pushing a button, you must wait until all pulses fully handled before pushing it again. Never push the button. Modules are still processing. Pulses are on in order. ABC, and then module A processes its pulse and sends more pulse. Have to in the order. Okay, so we have a FIFO. This each model and example. Okay, cat. Okay. Okay. And this module can be broadcaster has three destination modules, A, B, and C. A flip-flop module. A outputs to B, which to C. Outputs to another module named inv. Inv is a conjunction module. But it acts like an inverter because it sends the opposite type of. It outputs to A by pushing the button once. Following pulses, broadcaster has a low. Okay, and then A, B, and C. A sends a high pulse to B because these are flip-flops. Okay, B sends a high pulse to C. C sends a high pulse to the inverter. Now inverter sends. Because the A pulse sent a high to B, which sent a high to C, which sent a high to the inverter. Then the inverter sends a low to A. Okay, then A sends a low to B. Then B sends a low to C, low to inverter. Inverter sends a high to A. So pushing button again repeats the same sequence. Well, wait, that receives an A and A receives a high. Why wouldn't A receive a high? Wouldn't it send a high? So push. Oh, and then they settle, I guess, is what you're trying to say. And to always deliver. Okay. So if you send a high to a flip-flop, what does it do again? If it was off, it turned on. High, it ignores it. Okay, so these send high to the flip-flops. Oh, so the B is from the broadcaster. Okay, got it. Okay, broadcaster, two flip-flops, etc. Nope, push the button once. Okay, we can turn. What's the question? What do you get if you multiply the total number? Consumption will determine the number of low pulses and high pulses that would be sent after pushing the button 1,000 times, waiting for all pulses to be fully handled. What do you get if you multiply the total number of low pulses by total number of high pulses? Okay, I think I understand the problem. Now, let's see. So we are processing it in DFS. So first of all, let's load the input. So match of no space, space, arrow. Uh, these are just word characters, right? So actually, let's do it like that. $sign. Uh, uh, okay. Okay. Now for each of these, I need to store. So actually, let's do it like this because there is. Right, all of them have a symbol except broadcaster, right? Okay, yeah. So that's fine. I'll just call it broadcaster. $mod of $2 equals, and then we keep $1 is the type, and and then split by comma space of $3. Okay, let's call it H, and let's print out the hash. Let's run it. Make sure we parse the input correctly. Yep, okay. And we have broadcaster. Yep, okay. Now we need to do the following. We need to, okay, now we need another hash to tell us what state it is. So flip-flops have state. The conjunctor modules remember the time most recent pulse for each of their connected input modules. Updates its memory. Then if okay, yes, okay. So I need memory. So I need that will be the memory of the stuff. So I'm going to do the following. So we have a queue of signals to process, right? So for we need to run it 1,000 times. Now my list basically we need to my queue. So the queue starts with I need to send a low signal to broadcaster, as it conveniently is called. So I'm going to send a low signal to broadcaster. While queue, I need to process the queue. Okay, my E equals shift. Actually, my dollar signal node equals shift Q, but right, yeah, like that. So sigma is a signal and node, and then I need debug sig node. Right, let's get rid of this debug of hash. I want to see that. Zero Rodcaster, yep. Okay, now I need to process that. So by processing, I need to see based on the node type and what to do, right? Right. So, okay, so if my type equals a hash of $node of 0, and then if type equals b, then that's easy. I just broadcast it, which is for my, oh, let's make it, let's make it, let's do it like this. So type is that. For my next and h2 of node, so push q, so this would be the same signal, and the node is $n, right? Yes. Else if there are two other types. Type equals %, that's a flip-flop. So next, if unless $sig signal is 0, you don't do anything. Otherwise, flip-flops start in the off position. Yep. So memory of $node equals, yeah, reverse to its value. The signal is a reverse, and then send the new signal to everyone else. So push, send the new signal to the thing. Okay. Then the third option is the conjunction. So this one is interesting because this one only really does a one if it's all of number for each of the, and can update for that input. That how all inputs. Okay, so then I need something else. I need anything that goes to a conjunction module needs to be checked separately. So for my x in while p value equals each h, next unless value equals ampersand. I need to know how many there are and who they are, because otherwise there's no way to know. So next, memory of, so, so then I need to see everyone's, no, okay, shoot. No, H2. Now I need the following. For my $n in V, uh, next, unless $h of n equals an ampersand, memory of n of uh, $k equals 0. Yeah, that should work. And next, it's if it's ampersand. Otherwise, I need to remember that for that source. Okay, yes. Now I need to. How do I deal with that? Equals ampersand. So I do two things. First of all, I am. So I need to know where it came from, right? I need to know where we were before because I need to know where the signal came from, and that is not in the information. So I need to put that in there. My bad. I need to know where it came from. Sig node and prev. Yeah, these just push a node, but this needs to know. Okay, now I need to do the following. So I need to know, so memory of node of prev equals signal. Now I need to do the test. If all how does all uh, how does all work again? All block list. Okay. Okay. All block is just that in values, and the hash is m of node. So if they're all of them are true, that's what that means. That's what this checks for. Then, or actually, I don't need an if. I just need my out equals. So that's what I'm sending. And now let's send it that. Uh, Probably should have put that in a comment section, but no need to deal with that. Okay, and then, oh, and I need to, uh, um, for the thing, dollar counts of sig plus plus out product of counts. Let's see how many errors we have. Line 67. I don't want values on scalar. What? Okay. All so and so values. Oh, wait. Dollar M. 5,000. That's what's going on here. Uninitialized value and prevent calculation. Oh, okay. Yes. Rodcaster and nothing. What? Why are they all zeros? That does not look like correct. VL, no. And then it doesn't do anything, okay, because VL needs to go to LVZP, and it is a percentage. But we said, oh wait, we said next. Oh yeah, it ignores a high signal, not a low signal. Uninitialized value type, and okay, let's see what's going on there. That is line 55. My type is H of node. Yeah, so or die node equals $node. Rx, why is Rx not there? Rx is not there. Did I not download the full input? Let's okay, that's weird. Because Rx, let's read the description again. Rx, is Rx special? No. Uh, Conjunction modules. Okay. So I guess that's fine. I'm not sure what's going on. Why is there a module that I don't know about? Okay, this seems to be working. Let's disable debugging and hope that it runs fast enough. Right. That's fine. Okay, it's a little slow. Let's make sure we are making progress. Okay, is it making any progress? Because it seems like it might be stuck on the first one. Okay, that's a problem. Because it seems like we are in a loop here, and I don't like loops. At least not these loops. So, okay. Okay, let's see what is. Let's try a simple one, and let's get rid of the loop. No, okay. Da, da, da. Okay, so where's the more interesting example? That's it. Cat and 20 simp dot in. Okay, that is not what it was supposed to be. So let's look at the output and see what the mistakes are. So, following more interesting example. Button low broadcaster. Broadcaster low, it goes to A. Okay, A came from A high to inv. Oh, it's not. Okay, yeah. This is an inverter. I forgot. So, uh, this is an inverter, so it is not. And, okay. Is that the correct number? No. No, not at all. Okay, so again, let's see. Broadcaster, uh, broadcaster low to A high inv, A high con, inv low B, okay, con high output. I already don't like the fact there's output. Wait, con high output? Con is low output according to this. What is con? Con is an and con high. So again, A goes to inv con, B goes to con. That's again, it's not initially default member in the low pulse range input memory. If it remembers high pulses, it sends a low, otherwise it sends a high. Okay, yeah, that's what I thought. So let's again see why is this so so I'm looking at this step. So broadcaster button low broadcaster, broadcaster low A high to inv, and then A high to con in that order. Okay, yes, A high to inv, A high to con, then inv, low to B. So B got low from inv. Then con gets high. Why is it high? Because A sent a high to con. So yeah, so con should be high to output. Instead it says low to output. Okay, that's the problem here. So output, uh, let's output that and exit just so I can try this. Uh, A is 1, but where is the other one? Where is next unless H and I mean, okay. Why is this memory? Oh, $N. That's the bug here. Okay. Yep, that's a bug. That's a bug. Let's fix the bug and get rid of this. Okay, wrong output. Actually, let's keep that printout to make sure. Yeah, still bug. What? Okay, of n of k equals 0. So n is the one that is in ampersand, and k is the one that links to it. So let's see. What is the initialization completely bonked? Let's check that. Check the initialization. Uh, inv and con. Okay, cool. That looks good. But what is the node here then? Uh. Mhm. Okay. Uh. Mhm. That seems fine. The node is inv. Inv is fine. Oh, okay, okay, okay. Yeah, that's fine. And then con. Okay, and then con a. Okay, so con high output, B high con low output, and then okay, and then it runs it again. Okay, so that seems to be the right thing, right? So why? Okay, so that and the output is still completely wrong. So let's keep going. Okay, so I almost want to print it in the same format so it would be clearer. Con low output. You know what? Let's do this just so I can say the because okay. So so wait. So it's okay. Yeah, it's prev. just to make it look like that. Okay, so broadcaster low A low inv, A high, A high inv, A high con, inv low B, con high output, B high con low output. Button low broadcaster, broadcaster low A low inv, A high con high output. How many times is that? Oh, it is the correct output. Oh, it is the correct output. Never mind. That's why it's so difficult. Okay, correct answer. What time? It has a module attached named RX. Turns on when a single low pulse is set there. Go handle US number of button presses. Oh no, is this reverse engineering? It is reverse engineering. I'm sure it is reverse engineering, but I'm still gonna pretend it isn't. And yeah, this is reverse engineering. What's the minimum number? Okay, let's look at this because yeah, this is reverse engineering. Okay, Perl. So broadcaster. Actually, let's look at the existing code. Oh, when I put the debug stuff back in, first press sends a lot of high signals and then it sends a bunch of high signals to RX. A bunch of high signals, a bunch of high. Yeah, so this is probably some kind of counter. Let's see what goes to RX and then okay, so let's clean this up a little bit. Okay, what goes to RX? The only thing that goes to RX is DF, and DF is an inverter. So to send a a 1 to RX is the same thing as sending a 0 to, well, no, to have it's a NAND. So well, let's see. Does DF what goes to DF? DF gets input from a bunch of stuff, and in order for it to be 0, all of those need to be 0. So maybe there's some Chinese remainder there, but let's take a look. XL to DF, ln XP to DF, and GP to DF. So all of those need to be on in order for it to get that. Okay, and these are all and as well, sorry, NAND as well. So let's see, XL only gets input from this ZP. LN only gets input from this PP. Haha. XP, yeah, they all get input from one of these, and GP get input from one of these. Okay, so these send to a bunch of other stuff and to these. And remember, in order for Rx to be 0, all of these need to be 1. For all of these to be 1, these all at least, so for all of these to be 1, uh, wait, again, so these are just inverters. So, right, so for these to be 1, all of these need to be 0, and these are probably another one of the, another thing. Okay, ZP has a lot of inputs, oh my goodness. Let's look at PP. This, sorry, no, don't want to change the input. That will be bad. PP has a lot of inputs. SJ has a lot of inputs, etc. So, yeah, they all have a lot of inputs. Do I want to visualize this? Probably. Yeah, let's visualize this. um, as follows. So basically, this is a very okay. So I just need to do a very simple manipulation on it. So okay, let's look at this. So what I need to do is as follows. I need to remove the first letter. So say dgraph x. Then I need to um, uh, match first letter, rest of the letters. Okay. Now, and oh, actually no. First letter, first word, then the rest of the stuff. And what I want to print instead is a node with the illustration label equals uh, f and then r. Okay, there is a syntax here. 930. Okay. Still working on it.
Oh, really?
Yes.
Must
Okay.
it's a good one.
It's an interesting one. Okay. Well, oh, not P T. Syntax error. Line one. Oh no, I meant dot. Line two. Wait. How? Isn't that how dot? Uh, Wait. I thought that's how it works, right? Uh, it's just yeah. Oh. Okay. F it's this is one that you need to solve manually. What? Isn't that? Uh, what? Oh, okay. I think I know what's going on here. I need to do it like that. Yeah. Okay. Uh, R, R. What? That's not correct. Oh, yes, there is an arrow there that I need to get rid of. Okay. Okay. Oof. So there is B, and actually, Rx. There it is. Okay. Okay, let's look at this graph. Let's look at this mess and see what's going on here. So Rx, conjunction of a bunch of things. This is a conjunction, a bunch of flip-flops. So yeah, the bunch of flip-flops is a counter essentially. Okay, so let's call it NAND just to make this clearer to me. I know it doesn't matter. Okay, so NAND, all of these. And this is, wait, if the NAND and another NAND, that's basically just a NAND. So this could be removed and all of that turns into just more inputs to this NAND. And the same, more inputs to this NAND, more input to this NAND. Okay, so all of these NANDs go together. Okay, this is working because this is a bunch of counters. And okay, this is good. This is good. Because what's going on here is, and the flip-flops ignore highs and the flip-flops ignore highs and flip on lows. They start low, then the first time you press the button, all of the flip-flops are low, so they will all switch high. But then when you're NANDing here, you're NANDing all of these flip-flops need to be, all of them need to be high, which they will be immediately, no? Uh, yeah, you want them all to be high. But at first, you go into this flip-flop, and oh, this is something sneaky here. There is so when you go there, it will count, because, okay, so this NAND changes the flip-flop. So they will all be, at first, they will all be high, making that NAND be 0 and flipping the flip-flop again to reset that to 0. So only this one will be 0 and the rest will all be high. No, something is weird here. Cause, okay, so it seems like it will right away happen, but no. So let's again look at the original output pro. So what happens here? Broadcaster, our famous broadcaster, initializes these 4 starting flip-flops, and then these 4, all of these, so VL, which is I guess the first one, sends a high signal all the way, uh, V, etc. Okay, and then wait, VL, so sends it to the and sends it here. So, and again, the and needs all of them high, and then this, okay, it's CS sends, wait, shouldn't it send to the same NAND? Because it's going to this flip-flop, and then this flip-flop sends it to, because I'm assuming the VL and CS, just let me add to this input, just to make that a little clear. Okay, so yeah. Wait, Rodcaster isn't a percentage sign? Oh, sorry. I'll put it in the correct place. And yeah. Okay, so Rodcaster sends a hello to all of these. Now, VL is the first flip-flop, sends it to, let's assume it's this, could be this one, could be this one, they're all generally the same. Oh, wait, no, this is different a little bit. It sends it to LV and ZP. Now, the next one, oh, sorry, it processes it to BFS, right. So the second one sends it for a fourth one. Then ZP sends hi to a bunch of stuff because ZP is the NAND. No. ZP, yes, ZP is the NAND. So the NAND sends it to a bunch of flip-flops on the way here. What is going on here? And because I thought this is a normal counter, but this is a little more involved. Because the NAND sends a high. Okay, high, but that doesn't matter. High signals don't matter when they go to flip-flops. And the moment that all the NAND sends a, except it will when, okay. So what I'm thinking, I need to just simplify this so I can simulate a lot more button clicks, right? So goes to all of these flip-flops and flips them over multiple. So any odd button click doesn't do anything because, well, no, because they will send high, and sending high to the NAND, it won't matter much, and sending high to, so yeah, like this, let's look, the even button click, what does it do? It's, so they send a low, sorry, yeah, that's what I'm, wait, no. If the first button click made them send high, sending high doesn't do anything, right? So the only ones that actually matter, yeah, so XL, where did XL get it? XL get it from ZP. Okay, actually uh, let's change the visualization a little bit just to make this easier for me. Okay, let's do it like that and rerun the visualization. Okay. Again, so XL, where is XL here? XL is, okay, XL is one of the inverters. So the inverters send low. Why do they send low? Because they got, wait, they got high from the inverters send low because they got high from the NAND. Okay, which means, yeah, high from the NAND, which means nothing. And then these are all low and does nothing. So what's going on here? We're sending a bunch of lows to these flip-flops, turning them all high. Then, uh, then we are a bunch of, yeah, to flip-flops, turning them all high. Then, uh, and then these send a bunch of highs. Actually, let me remove, don't print out even when you send a high uh, to a another flip-flop because I don't really care uh, unless type equals percent and sig. I don't care if you're sending a high to a flip-flop because it's ignored anyway. So yeah, type O and sig. Okay, much smaller. So broadcaster turns on VL, CS, etc. the first flip-flops in each of these, and then they send high to a bunch of ends, and that's it. All happens in first press is these flip-flops turn on, and that's it. Second press, so we send low to these flip-flops again, broadcaster sends it, and then we send them to ands, uh, and we flip the next flip-flops in line, right? And now we need a loop of flip-flopping to do that because, yeah, this is, because this is a, okay, so this is essentially, what's going on here is this is a counter going to a specific value, and the binary value is determined by these. Let's, actually, let me just try this and figure out when these ands are on, and then I can, yeah, let me do something like this. Say I, and now I'm gonna check, uh, okay, and now I'm gonna basically just check these four flip-flops, sorry, four and markers, ZP, SJ, RG, and ZP, SJ, RG, PP. ZP, RJ, RJ, SJ, ZP, RJ, RG, ZP, RG, SJPP. SJPP, those are the ones, okay, and for my X in that, uh, if memory of X, if this is, if uh, this, if the NAND is happy, that's what's going on here. If the NAND is happy, say X happy at $I. Okay, and then let's run it again. Uh, let's remove some debugging outputs. That's what I was afraid of. None of them are happy yet. So let's see. Any of them, yeah. I need a bit. None of them are happy, huh? I'm kinda surprised. I figured I could just reverse engineer it partially and see this, but this is not quite working, huh? Interesting. Because this is, yeah, CP, SJ, etc., etc. Huh. That's interesting. Let me think about this. I thought for sure this would be, okay, none of them are happy. Uh, and yeah, this is correct. This is the what we're looking for, and none of them get happy just in a quick check. So I'm getting all of it. I thought they would all have like shorter loops, and then I can figure out when they're all happy. But for that, but even none of them are happy, which is surprising to me. I guess. Like how many flip-flops we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 bits. That's only like a few thousand. That should happen faster than this. Something is wrong here. Something is definitely wrong here. First of all, let me double check that we're not that I didn't mess up the input. Is this still the solution to part one? Uh, yes, it's still the solution to part one. Okay, so our code is still fine. Now, if all I underscore of values of etc. is true, then that one is happy at I. And the thing is, it's never happy because, and the thing is, it should be at least in 2 to the 12, it should happen once. Like, right? No. Okay, so, yeah, so there is something weird here. Let's go back to the thing. Because, yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of these. Yeah, I'm just looking at ZP. And, and yeah, remember? Just, I want to just check that it is, that that the code is correct because, uh, yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me just follow a single one of them just to see how this goes. Mr. ZP. Okay, this is 1, 1, 0, 1, 0, 0. Yeah, so this is counting. Wait, now they're all zeros again. But if they're all zeros, that should... Uh, no, we're looking for all ones. But that never happens. Uh, Wait, how we got to the we got to a situation where they're all zeros. That's interesting. How did that happen? Because it comes back and flips the oh. It happens in intermediate cases. I see. I think I know what's going on here. Basically, I need to see. Okay, and then it would be. It will never be happy at the end of a thing. It will be happy in the middle of a button press. And that's why it's annoying. Okay. Oh, actually, any of the ands are interesting. Well, except the negators, I guess. Yeah. The node is interesting, and yes. Okay. That's what I was hoping for. So, ZP, RG, PP, and SJ. RG, PP, and SJ, and those are the numbers, just multiply them. 38, 33, 40, 21, 40, 51, and 40, 57. Make a huge number, which will be the answer. Correct.